efficiency calibration of the sodium iodide detectors for measuring the carbon-12 N2N and carbon-11 cross-section.
Thank you. Today I'd like to talk about an experiment that was performed at Houghton College to measure the efficiency of sodium iodide detectors in order to make a measurement of the carbon-12 N2N, carbon-11 cross-section. This is a photograph of an inertial confinement fusion chamber, in fact the one over at the laboratory for laser energetics right down the road. In an inertial confinement fusion reaction, a pellet of nuclear fuel is compressed using high energy lasers. That compression induces fusion reactions which then release neutrons. Now we can learn information about the reaction, such as the isotropy of the reaction and the fraction of fuel consumed, by looking at these neutrons emitted from the reaction. Now one way of looking at these neutrons is by allowing them to activate a carbon disk, which we set in the chamber. However, in order to use this method, we need to know that for a carbon atom, what is the likelihood that an incoming neutron passing through the disk will activate the carbon atom by the carbon-12 N2N carbon-11 reaction. So what we need to know here is what is the cross-section of the reaction, which is proportional to the likelihood. Now, this is a plot of the previous measurements and calculations for the carbon-12 N2N carbon-11 cross-section, with the cross-section on the y-axis as a function of the energy of incident neutrons. Now, one problem that we face here is that in the region of interest, there's disagreement by up to a factor of 2 between the different measurements. So we needed to make a measurement of the carbon-12 N2N carbon-11 cross-section that was better than these current measurements in order to use our diagnostic technique. We began that process with an experiment at Ohio University. This is a photograph on the bottom and a diagram at the top of an experiment that was performed by Houghton College students and students at SUNY Geneseo at Ohio University using their tandem Van de Graaff accelerator. A beam of deuterons was shot at a tritium target, releasing high energy neutrons which were incident on a plastic foil and a carbon disk. Then we were able to find from the NP scattering off the plastic foil and using a proton telescope what the neutron flux for the experiment was. Now the plastic foil and the carbon disks were removed from the experiment hall and placed between 2 sodium iodide detectors. The carbon-11 in the disks, after the disks had undergone the carbon-12 N2N carbon-11 reaction, beta decayed, releasing a positron, which then annihilated in the disk, producing 2 back-to-back 511 keV gamma rays. Now on the bottom you can see a photograph of that experimental setup. At the top, sort of a rudimentary diagram of what was going on. We needed to measure the gamma rays in coincidence at the same time when they get into both detectors. However, not all of the gamma rays emitted go into the detectors. So, in order to use this as a counting mechanism, we need to know what fraction of the total gamma rays are measured in our detectors. That is, what is the efficiency of our detectors? Now the first experiment we performed to measure the efficiency involved, and you can see here, there's a photograph on the right-hand side and a diagram of the simulation made of that experiment in the GEONT code on the left-hand side. On the right, you can see here, with the experiment, we used a sodium-22 source, which beta decays. The positrons released by the beta decay annihilated, producing back-to-back 511 keV gamma rays, which were able to be counted in coincidence using the same sodium iodide detectors from the earlier experiment. Now, an additional sodium iodide detector was used because the sodium-22 releases 1275 keV gamma rays, and we needed to make sure that in our measurement we weren't getting events where that 1275 keV gamma ray was going into the detectors that we cared about. Now this is a plot with efficiency on the y-axis and as a function of the distance between the source and the detector. We have the detectors themselves and we move the sources forward and backward, or the detectors forward and backward. And the blue curve here is the simulation, which you saw in the picture on the left-hand side earlier. and these are experimental data points in orange. The root mean squared percent difference between the experiment and the simulation was 2.5%, which we determined to be adequate for what we were looking for. The second experiment we performed used a source of germanium-68, which was calibrated such that so that we would know what the decay rate per unit of time was within 1.7%. And we also modeled that using giant simulation. Here's the image of that on the left. Now, for our results, we had both data sets where we moved the detector further and closer away from the source. We also moved the source parallel to the face of the detector. And at the top, that's where we're moving the detector. And of course, again, we have the blue curve from the simulation, and the orange plots from the experiment. You have the efficiency on the y-axis, and then the different distances on the x-axis. The root mean squared percent difference for these experiments was 2.8%. That's the difference between the experiment and the simulation. Then for experiment 3, we wanted to include the effects where gamma rays were able to essentially scatter off of the electrons in the carbon disks. Now, so what we did is we sandwiched our germanium-68 source in here between these carbon disks, and then also simulated that in GEONT. What we found for several different experiments, this first experiment where we had one thin disk of carbon on either side of the germanium source. And this second experiment here where there was one disk on one side of the source and 3 disks on the other side of the source. We wanted to see if we can include asymmetries in our simulation. And at the bottom here, we had 3 carbon disks on either side of the source. This was pretty much equivalent to what we had in our Ohio University experiment, the thickness of the carbon disk. Now, and the RMS percent difference was 4.3%, which we determined to be adequate. Now, once we had calibrated our GEONT code using the experiments, we then used that GEONT simulation to determine the efficiency of the original Ohio University experiment. Then we could go back and see, well, how many carbon-11s were in the disks during the experiment. Using that information, we produced preliminary carbon-12 end-to-end carbon-11 cross-section measurements. And so what you can see here plotted is the cross-section on the y-axis and the neutron energy on the x-axis. And we have points where we have both coincidence efficiency, where we have both detectors going off at the same time. We also have plot points for singles efficiency, where we only require that one detector go off at a time. That is sort of a check for the validation of our method. What we did was, at least to some degree, accurate internally. Now, this is a plot of our measurements compared with the plot that I showed at the beginning of the talk of previous measurements. And what we found was that our data had a root mean squared percent error of 6.8% and a statistical error of 5%. I'm sorry. What was it? It was smaller than that, but not a statistical error. And so then these plot points, we're still examining these, but we will be publishing them in an upcoming paper. And we seem very happy with the results. Thank you. Are there any questions?
How do you know the gamma is 511K?
So the positron has the electron rest mass of 511 keV gamma. Well, a positron has an equal rest mass, and what you have is when the positron and the electron collide, when they annihilate, they need to conserve momentum, and there's no velocity when they begin to annihilate. So you can kind of think of it, if if you were in a very narrow hallway on a rolly chair, and you needed to exert your energy, you need to push on both walls at the same time. So you need to release your energy in opposite directions in the same amount, right? So you cut the total energy in half, and you still get the same 511 keV of gamma coming out of that.